Hi everybody, this is Mrs. Peachy from your physical science class, and I'm going to be doing a little bit of a tutorial supplemental on the periodic table today, and kind of looking at how to make dot diagrams, because that's something that we didn't have a chance to go through in class, and I think it's pretty important, and since we do have some time off here before our next class, just want to make sure you guys know what you're doing. So I am going to direct you down to my handy dandy notebook, and I'm going to do a little flipperoo of the screen for you. Okay, and then I'm also just going to quick put this so that we have full screen. Alright, awesome. So if you look at the periodic table, and I've brought this to your attention before, but if you look at the periodic table, there are a lot of different relationships here that are kind of important. But one of the things that we talk often about is the number of valence electrons in each column of the periodic table. We're only looking specifically at the first two columns and columns 13 through 18 right now. Those are a little bit easier to work with, but they match the column number. So 1, 2, 1 valence electron, 2 valence electrons, and then we have column 13 has 3, 14 has 4, and so on. So that's information that I told you guys in class earlier. Now, if you remember, a valence electron is the electrons that are found in the outermost shell of an atom. And those are important because those are responsible for chemical bonding. And they're right there and available to bond with other atoms. So what we look at when we're kind of creating a shell diagram is we just look at the electrons in the atom itself. So if I bring up a periodic table again and I select one of these, for example, let's look at beryllium. If you look here, beryllium has an atomic number 4, which tells us that it has 4 protons. It also has, if I looked at the atomic mass, it has 5 neutrons and it has 4 electrons. But I'm only concerned right now with the number of electrons because I'm just going to be graphing that. So there's what's called a shell diagram, and then there's dot diagrams. And the shell diagram basically would just put, you would just have a nucleus here, and I would write a B, E for beryllium in the nucleus. And then I would also then put in the number of electrons. Now, one of the things I reminded you of is the formula 2n squared. That tells us how many electrons are found in each shell of, or how many electrons each shell of an atom can hold, the maximum until it's full, okay? And really, we just look at the first 3 shells for the most part in physical science, so we're not going to go much past that. But the idea here is that the first shell is shell number 1, so 2 times 1 squared. 1 squared is 1, 2 times 1 is 2, so shell 1 can hold 2 electrons, okay? Shell 2, 2 squared is 4, so 2 times 4 is 8. Shell 2 can hold a maximum of 8 electrons. Shell 3, 3 squared is 9, 9 times 2 is 18, so shell 3 can hold a maximum of 18 electrons, okay? So that's the maximum until it's full. But then we have the rule of octet, or the octet rule, or the rule of 8s, or I call it the magic 8 rule. This tells us that the maximum number of electrons in the valence shell, and remember that valence means outermost, is 8. Okay, so this tells us that if the outermost shell is the third shell, it can't have 18 electrons in it. It can only have 8. If it has more than 8, they get bumped up to the 4th shell, okay? But right now we're just doing beryllium, and beryllium has 4. The first shell only holds 2, so we can put in 2 electrons in that first shell. And since it has a total of 4, the second shell is going to contain those other 2. Okay? So this kind of gives us a picture, a shell diagram of beryllium. Okay, pretty easy, right? When you look at bigger elements, it becomes a little bit more complicated. If I go up to, say, potassium. Potassium has 19, atomic number 19, so 19 electrons. So if I go here to potassium and I draw the nucleus and I label it a K for potassium, right? And I'm going to draw some shells here. So remember that first shell holds only 2 electrons, okay? So we have 19 total. We're going to put 19 in there. So the first 2 goes here, okay? So now we have 17 left. The second shell is going to hold 8 electrons. So 1, 2, oops, 1, 2, sorry about that. That's 3, 4, 5, 6, 7, 8, okay? So 2 plus 8 is 10. So I have 9 left now, right? The third shell can hold 18 electrons. So if I put all 9 in here, if I put one more to make 9, that violates the octet rule that says the maximum number of electrons in the valence shell is 8. Remember, the valence shell is the outermost shell that has electrons. So we can't do that because it would be a violation of that rule. Instead, we bump that last one up to shell 4. So now we know that potassium only has 1 valence electron. Well, look at this. Potassium is found in column 1 of the periodic table. So that tells us right there that we should have done that, okay? So this is called an electron dot diagram. There's an easier thing to do, though. These are called Lewis dot structures, or they're often called, sometimes they're called dot diagrams, too. So in this case, for potassium, since it has 1 valence electron, we would put a K for potassium, and a single dot. And it's done. There's your Lewis dot structure, or Lewis dot diagram. Okay, so pretty cool, right? Pretty easy. So if we're doing one here for, say, I don't know, aluminum. Aluminum has 3, right? So aluminum would just be 1, 2, 3. You can rearrange those dots if you want. Remember, they do tend to form pairs, okay? So that's pretty cool stuff, right? I mean, that's pretty simple. Now, we can use these Lewis dot diagrams to form some fun compounds, too. Sodium has 1. Column 1. Chlorine has 8, or 7, excuse me. So now we have 8 around here, right? So that's good. That gives us sodium chloride. Okay, so they bond together because they stick together like that. Not exactly the best way to show that. We're going to talk about ionic bonding next time. But we do use those to help us form different compounds, primarily covalent compounds. So All right, guys, so hopefully that helped explain that a little bit to you. I know we didn't have enough time in class today, so hopefully that makes some sense. If you have any more questions, this is a giant picture of myself. Feel free to give me a call at extension 2204 or send me a webmail message. Have a great day, everybody. That's a little better. Bye.